Hello everybody, we will continue our lectures on this optimal control guidance and estimation course. So far we have covered a variety of topics, both theory and applications as well. So towards the end of the course I thought it is also a good idea to see a slightly different topic. It is very connected, but slightly extension of the topic in a different domain, which is called distributed parameter systems. Okay. So, I thought 2 lectures I will cover some topics on optimal control of distributed parameter systems, and especially the research that we did and the results that we got some time back and things like that actually. So, let us get started. This is the topic what we want to discuss in these 2 lectures. This is something called distributed parameter systems. Essentially these are the systems governed by a set of partial differential equations. And so far we have not talked anything about that. We talked everything about system dynamics in ordinary differential equations in state space form. So, that means these are the ordinary differential equations represent something called lumped parameter system, whereas this partial differential equations or PDEs they represent this distributed parameter systems. Okay. And such class of systems arise very naturally in a different variety of application problems. First thing is, let us say you talk about heat transfer process. You can talk about something like a lumped parameter behavior of heat transfer process. By the way, what is lumped parameter system? It talks about something like a system where there is no relative dynamics between different molecules of the system. That means, if one particle goes, everybody goes together and things like that. They do not relatively disperse out, they do not there is no relative dynamics between the 2 molecules of the system actually. That is lumped parameter system. Whereas the distributed parameter systems that has a special behavior also. In addition to temporal behavior, that time evolution, it also has special behavior, and hence we need more than one independent variable to describe the system dynamics. That is why we need PDEs. And then the example problems include heat transfer process. The moment there is a heat somewhere, it has to dissipate everywhere in all directions. So, that has to be talked about that sense. Then the fluid flow problems, both in liquid as well as gas form. And then you have this chemical reactor processes, where this chemical reaction takes place throughout the reactor basically. So, that the dynamics of that is typically governed by partial differential equations. Then there is something like vibration of structures, and in aerospace maybe aeroelastic problems like that. So, you see there are various problems, including probably ecological problems also. Sometimes this behavior of this small animals in the jungle and all that, in search of their prey, mate, all sort of things, they go in different directions. And then if you really want to see the dynamics of this entire behavior of this entire colony, then probably we need PDE, partial differential equations also. You see there are variety of problems that cannot be kind of categorized as lumped parameter system. We have to talk about system dynamics in PDEs only. Now, the question is, how do we control these systems? Okay. So, and how do we optimally control these systems? So, these are the questions that arise naturally, and then there are techniques available also, and we will seek 1 or 2 techniques as we go along in these 2 lectures actually. And when somebody talks about control of distributed parameter systems, 2 things comes into mind. Remember, these are something called infinite dimensional system also. Means if you really want to have the behavior of all molecules of the systems independently, let us say, in some sense through constraint equation for their relative behavior, but each of the molecule will take their independent dynamics, then obviously we have infinite molecules in a system, and hence it is infinite system, infinite dimensional system. And if you really want to kind of approximate it through some sort of approximate lumped parameter system, then through this modal behavior, first mode, second mode, third mode, things like that, then also we need infinite number of modes actually. So, that is in that sense it is also infinite dimensional system. So, that cannot be done, that cannot be handled. So, there are ideas like something like design and then approximate. That means you invoke this infinite dimensional operator theory, and then do all sort of algebra math and all that, and finally come up with an infinite dimensional controller also basically. And obviously you can't implement that, or the feedback necessary is also infinite dimensional like that. So, then you cannot implement it that way. So, finally you have to approximate. Okay. So, first you design and then you approximate. On the other hand, naturally the other thing comes approximate and then design. Okay. So, this approach what you see is design then approximate, it is typically favored by math people. The mathematics people will typically like to have this, whereas engineering people will typically like to have this actually. Okay. Theoretically, this is more elegant because it does not talk about throwing away behavior to begin with at all, and the implementation is subjected to only your computational power and things like that. Implementation, practical difficulty, origin and computational power. Whereas this one, the system dynamics itself is truncated from to begin with, and hence there is an approximation to begin with actually. Okay. But anyway, so this is typically favored by engineering people, and then this itself can be divided into two ways. One is design without model reduction, means you design some sort of you put large uniform finite grid sort of thing, and then do not do any model reduction sort of thing, you just directly use that and go ahead and design the controller. That is one way of doing this, but then it also requires a large number of grid points to do the problem, to solve the problems in a satisfactory way, and hence this is also not good in general. So, what people think is okay, we will approximate, but then introduce this model reduction concepts also. So, that we have to handle this low dimensional lumped parameter approximation of the system dynamics, and then carry out the engineering design or the control design based on that reduced order model actually. So, these are the various categories that comes to mind. Okay. And we will typically see this side of the story, engineering side of the story, both design without model reduction and model reduction also basically. Okay. So, this is how it is, and the topics that these two lectures typically will talk about LQR design. Okay. So, if the system dynamics happens to be linear, that means the PD itself is linear, then it will result in approximate lumped parameter system which is also linear. So, and the cost function is quadratic, then it also result in a finite dimensional cost function which is also quadratic. So, that will have a compatible LQR formulation, and hence because we know LQR formulation, we can go ahead and implement it actually and solve it and implement through Rigaud equation, all that. So, we will not talk about philosophy here, directly we know the philosophy. So, just I will demonstrate this idea through some examples. I mean just one example I will take. So, then we will have some I mean your ideas will be clear actually. And then we will digress slightly a little bit. I think it is it's a slight digression in some sense, but it is overlapping with optimal control in a way. So, here I will talk about something called optimal dynamic inversion. Again, that is something that I mean we proposed some time back. So, that is not really optimal control, but there is optimality aspects that comes on the way, and variational calculus is also used on the way actually. So, these two we will see, and especially this lecture will cover these two, and the next lecture will come back to this single network adaptive critique. Okay, that is something sometime back we talked about that, and in that framework we would like to solve this problem for optimal control of nonlinear distributed parameter systems or nonlinear I mean PD sort of cost function, I mean system dynamics and associated cost function, using directly like finite difference, or using this model reduction ideas like proper orthogonal decomposition like that, and then synthesize a controller, and then obviously on the way we will give examples also basically. So, this lecture, these first two topics, and next lecture I will cover this SNSE based optimal control design. So, let us get started. First thing is optimal control of linear distributed parameter systems using LQR and finite difference. This is a very simplistic idea that comes to mind, and probably that is the, I mean more than that I mean it may not happen actually. Okay. So, let us just a small demonstration of the idea through an example, and through that I think everything will be clear to you actually. Okay. So, let us talk a simple linear PD in this form. Okay, del x by del t is del square x by del y square plus u of t y. So, this x is the state, okay, but it is a scalar problem, x is a single state I mean x is a single state. However, it is a function of both t and y. Okay. So, t is the time part, how it evolves in time, okay, and so if you have something like y varies from let us say 0 to L, okay, that is the y part of it. So, x is there everywhere along y basically. Okay. So, but then the behavior of that, suppose you want to take t equal to 0, then something like this is this probably t equal to 0, then t equal to let us say a little bit later t plus delta t, this is something like okay, t1 let us say, it can be different things actually. Okay. So, this is the type of problem that you are talking, and we are also assuming that control is available throughout the domain 0 to L basically. Okay. So, control is a continuous controller actually. Typically, that is one of the difficulty of distributed parameter systems. We can't have a continuous control action throughout the domain actually, that implementation says it is not possible in general basically. Alright, so we have a system dynamics this del x by del t equal to del square x by del y square plus u of t y. Still, it is a linear differential equation, linear PDE actually. Okay. And as initial condition, when t equal to 0, okay, we take some profile. Remember, t equal to 0, it cannot be just a number, it has to be a profile across y. Okay. So, something like that. Okay. And the boundary conditions must also be given in PDEs actually. So, at y equal to 0 and y equal to f, what you are assuming is that the derivative is 0, spatial derivative is 0, and that is something called Neumann boundary condition like that. Okay. Now, the task is to find a control u of t y which minimizes the cost function this way. Okay. So, again the quadratic cost function q and r are I mean scalars essentially here. Okay. And then this remember this is a double integral here actually, integrated with respect to y and then also integrated with respect to time. Okay. Alright, so this is the thing that we want to minimize. Well, ideally speaking, it should be y first and t next. I mean this either way. I mean mathematically both are equivalent anyway. Alright, so this is what it is actually. Now, how do you go about it? The very simplistic idea is, well, I will do this spatial discretization, let us say. Okay, I will do this spatial discretization. There is some grid points I will select. Okay, 1, 2, like that actually, up to n minus 1 and n. Let us say I will select it that way. Okay, this is right, n minus 1 here and n here. Okay. Now, what it tells us actually? Suppose I want to have this at any point of time, I fix a node, let us say I, okay, and that I at point I want to see this partial differential, I mean this partial derivative. Okay. How to approximate that? I will approximate that using let us say central difference formula, and central difference formula tells me that at any point of let us say y equal to yi, okay, these are all i's basically, this is I, then this is I actually. Okay. Alright, so I will take 1 plus here, okay, 1 minus here, this is central difference formula, we know it very clearly actually. So, this is I plus 1 and this is I minus 1 actually. Okay. So, this can be I mean very easily seen actually, at any grid point I can approximate that in this way. Okay. Alright, these are print mistakes actually. Okay, xi plus 1. Anyway, so now we include this notation. Okay, del x by del t. Okay, is xi dot, because after we discretize there is no spatial derivatives per se. Now, these are all node point values now, and then we can talk about something like partial derivative with respect to time as xi dot actually. Okay. So, if you do that, then what it turns out that xi dot I can represent coming one portion from here and then ui actually coming from system dynamics here. Okay. So, then if I repeat this exercise for 1 to n, what do I get? Everywhere I will put this kind of formula, then what do I get? I will get something like x1 dot, x2 dot, x3 dot, up to xn dot actually. the thing to note here is something like I mean everything is alright, but other than these two values are outside actually. Okay. X 0 and x n plus 1. When you see this, okay, we have a grid point from 1 to n, 0 is not there. So, what we do is okay, we will approximate that there is a fictitious node point, we will take call that as 0, okay, extend that little bit, and here another fictitious node point, call that as n plus 1. Okay. So, that is necessary for writing the system dynamics at grid point 1 and n actually. Okay. Now, the question is how do you get a value for that? These are fictitious node points anyway. So, this is where the boundary condition comes very handy, and then you tell okay, at y equal to 0, I will use something like backward difference. Okay. At y equal to, so for y equal to 0, I will use backward difference at y equal to 1. Okay. Here I will use backward difference at y equal to 1, and then here I will use forward difference at y equal to y n actually. Okay. So that then I will get this boundary conditions implemented this way. So this will tell me that because this is 0, then x 1 has to be x 0 and x n has to be x n plus 1 has to be x n. So then if you go back and substitute this is nothing but okay, this is from boundary condition what we got is this is nothing but x 1 and this is nothing but something like x n. Okay. So now we can simplify the first and last equation and then combine them together basically. Okay. Then it results that first equation and last equation, typically first equation happens to be this way, last equation happens to be that way, but all other thing will have a uniform structure actually. Okay. So now we can clearly see that okay, if I really want to combine everything, okay, I can combine it this way, okay, because now I can define a state vector and a control vector also, right. I mean, I can define a state vector with my grid point values x 1, x 2 to up to x n, and then I can define a control vector with the same grid point values as something like u n actually. So, if I define these two, then with respect to these two variables, I can write it this way, x dot is equal to x plus v u. Okay. Where a and v can be defined that way. So, we have got an equivalent representation of the PD in terms of ODEs. Okay, with respect to the grid point values. Okay. So, the more the number of grid points, the better the system dynamics representation, but beyond a certain point it may not be necessary also. And also it turns out that it not only depends on the system behavior, system dynamics, it also depends on the initial condition actually. How many grid points you need and things like that. We will give a small example and that will make your idea clear. Now, this is also very, somebody interested here, you can quickly evaluate the eigenvalues of this matrix A and you can realize that this is actually a stable system behavior, because this what system dynamics that we started with is a dissipative system actually. Okay, it represents a dissipative system. So, obviously, it is a system dynamics that will represent in stable behavior of this system dynamics in lumped parameter system. That means, the eigenvalues of A will all remain in the left hand side. You can quickly verify it actually. Anyway, so system dynamics we have got some representation in ODEs. How about cost function? And that is also even easier, because cost function all that we have to do is just use trapezoidal rule, let us say. So, we have this cost function to begin with. Okay. So, we use this special integral, whatever you get the special part of it. Okay. This special integral we will use trapezoidal rule, and trapezoidal rule will give us this one. Okay. This is like trapezoidal rule tells us that okay, is nothing but delta y by 2 h by 2 into first node values and last node values, and everything else will be multiplied with 2 actually. Okay. Half h into a plus b plus all these a1 a1 a2 like that way. So, you can revise this trapezoidal rule. We have also talked about that in our one of our early classes actually, the review of numerical method, I think lecture number 3 probably, you can look at it. Anyway, so using trapezoidal rule, you can put it back and then it results in a equivalent cost function in this form. Now, combining the values, variables and all that actually. Okay. And remember this 0, wherever we get a 0, that represents the x 0 represents is equal to x 1, what I mean, and x n plus 1 represents n and things like that way. Anyway, so details you can see it or you can derive it yourself, but ultimately it happens that you can write the cost function in this form actually. Okay. Probably there is a small thing here. I think the fictitious nodes are not required here. It is the directly node point. This is 1 and 1 and n. Okay, and probably this will start from 2. Okay, then it is alright probably. Okay. So if you see this in a picture, I mean this dynamics only requires a grid point, but evaluation of integrals, this starts from 1 to all the way up to n minus 1 and n. Okay. So the first grid point and last grid point are taken as it is. So this is 1 and this is 1, and okay, this is square also by the way. Okay. So these terms, and then all these things will be multiplied by this 2 actually, okay, because essentially it talks about area evaluation and things like that. So this will talk about that, and then this way 3 and then this 4 like that actually. So essentially it evaluates the area under the curve and things like that. That's why it happens like that. Okay, so coming back to that, this is okay, this is 2. Okay. So from 2 to n minus 1, it is twice the same value, I mean in the integrand value, and first and last point we don't have to worry about it. Okay. Now all these things can be again rearranged rather, and then you can represent in this form actually. So once you represent in this form, and the system dynamics can be represented that way, obviously it formulates an LQR problem actually. Okay. System dynamics is linear and cost function is quadratic. So this is an LQR problem, and we know how to solve it actually. So that is one way of doing that, and then you can see, okay, what does it give? It gives solution at the grid point values only. It doesn't give anywhere else actually. Okay, but that is all right. Still we get some idea about what is happening at the grid point actually. Okay. An example problem, if you take finite time, okay, LQR problem also requires either TF is infinity or TF is finite time. Remember that. So this example, the solutions or the results that you are getting, I mean that we have included is with respect to final time. Finite final time. So we have this TF is 1, YF 4, and all these values, numerical values are there. So I suggest that you verify these matrices that you are getting here. Okay, and then you code it, and then using MATLAB LQR function, you can actually recover the results yourself actually that way. Alright, so we have got the A matrix, we have got the B identity, we have got Q and R this way. So we incorporate LQR function and solve it. So what remember, MATLAB LQR is geared towards infinite time. Here you are talking about finite time LQR. So probably you have to do little bit coding to get it done. So you know this final SF equal to, I mean 0 in this case, because the outside thing is not there. So PF equal to 0, but P dot is the Riccati equation, and then you have to integrate it backwards from 1 to 0 and then implement it forward like that actually. Okay. We do all that, and then the case B we have taken a slightly different way. Okay. Okay, case 1, if you can see the dimensionality is increasing, that means the number of nodes are increased actually. So here the delta y is 1 and there the delta y is 0.5 actually. Okay. So now let us see what difference you get actually really. Now surprisingly there is no difference actually. Either you take it 1 or I mean either 5 grid points or 10 grid point, doesn't matter. These results that you take, I mean what you see is taken from here, this particular book. Some of the concepts in this lecture I have taken from this book. So this particular sort of behavior you can observe, and it really doesn't matter whether you have 5 grid points or 10 grid points, both will be same actually. Okay. And that happens because there is a linear profile here, okay, for which the special derivative turns out to be 0. Okay. If you take del square x by del y square, then there is nothing but 0. So initially, as long as you have a linear profile as initial conditions, this kind of behavior is expected actually. Okay. In fact, if you have a constant initial condition, even one grid point will do the job. That's what it is actually. Okay. If just initial condition is constant everywhere. Okay. Then if you take 10 grid points, solve it, 5 grid points, solve it, doesn't matter actually. Okay. So again, I mean this depends on that kind of thing, but when you get a solution, you don't want to confine yourself to any particular kind of initial condition or initial condition profile actually. So you let it be arbitrary, and then you may need a large number of grid points actually to get a reasonably good solution. The whole idea is start with a coarse grid point, let us say 5 grid points like this, and then go to 10, then go to 15, 20 like that, and somewhere you will see that the results are not different actually. Then you can say that okay, that is the final grid point I will select and then carry on. And in a typical example, in a real life example problem, you will probably require thousands and thousands of grid points actually. I mean that's the drawback of that, and hence this dimension of these matrices will blow up. Will end up with a very high dimensional representation, ODE representation of the PDE phenomenon actually. Okay, so that's the problem there. But essentially it outlines the idea that okay, we given a distributed parameter system, system dynamics in the form of PDE, we can actually do it. I mean there is now it's a question of how to do it better basically that way. Okay. So rest of the time on this lecture, let me digress to a slightly different topic. This is something that I want to discuss is in the framework of what we call as optimal dynamic inversion. It's not really optimal control, it's largely it will fall into the framework of dynamic inversion rather, but there is optimality concept included in that, and hence there is a weak link for optimal control also basically. Now, largely the material is taken from here, and then especially the very first one which appeared in 2007, and followed subsequently we have extended the work to a different class of problems in a little more real life problem of vibration suppression of nonlinear beams. It's essentially a structural control problem, okay, using this approach actually. This particular thing lays down the theory, lays down the ideas, and then solves an example problem that I will talk today. Okay, but this also you can see very similar concept, but it is used for a different problem. Remember that the difference is, now if you talk about something like heat dissipation or something like stable system dynamics, fluid flow or heat dissipation like that, these problems are relatively rather easier. Okay, they are something like some parabolic distribution, I mean parabolic differential equation actually. But when you go to vibration sort of thing, these are typically, I mean I think elliptic or hyperbolic differential equation. They don't die out so easily actually. I mean they will continue to vibrate until unless there is a good amount of damping and all that actually. So in that sense, it becomes a little more challenging problem really actually. Okay. But anyway, we are bothered about the ideas here, so we will concentrate on the first one. So in this one, there are two different things here. One is using continuous actuator, okay, which is more theoretical elegance, and then using discrete actuators also, which is practically more relevant. Okay. So if you have guarantee of continuous actuator, that means actually anything that you can do throughout the spatial domain. Okay, very next to it something you can do, very next to it something you can do like that actually. You have distributed actuators really. Then you can do many good things, and those are basically theoretically more elegant actually. Okay. Alright, so this is first we start with problems like that with continuous actuators. So the motivation is something like this, quickly to summarize. Distributed parameter systems are usually difficult to control in general. Existing techniques, design then approximate or approximate then design. Okay. And then this is the relatively new technique, I mean compared to what you see here. Okay, this is what is available. Okay, design then approximate, use functional analysis approach. Okay, this is typically mathematics people will want it, like to see that. And then this approximate then design, this typically this spatial discretization, that's what we just talked about through an example problem. Then there are other ideas like Galerkin projection approach through this modal analysis and all that. And this modal analysis can be extended possibly through the POD basis functions and things like that, which we are going to talk in next class. Proper orthogonal decomposition like that, where there is the idea of model reduction actually. Okay. So like this, if you can bring in, then this is approximate then design. But here is a technique. What we want to claim is something like falls into the DTA category. Okay. But without math complexity. Typically this is mathematically complex analysis, and hence it is not very much appreciated in engineering domain. But here is a DTA approach, okay, design then approximate category without too much of math complexity. The whole idea here is use something like dynamic inversion. Okay, again this details about dynamic inversion, if somebody is interested, you can see the lectures in my other course in NPTEL program. So they are there actually. Okay. Then here we bring some variational optimization theory, and that is what is used in optimal control. Okay. So, we put it together sort of thing to propose a new technique. Okay. And then we can also claim that steady state convergence can also be proved, okay, as long as we have this continuous actuator sort of thing actually. Alright, let us get started. To simplify things, we want this system dynamics in this form. Again, it is a kind of control affine form. So, x dot is represents del x by del t. Okay. It is not really something like lumped parameter system. This one is something like del x by del t. Okay. And when you see the x prime like this is something like del x by del y. Okay. When you see this one, this is something like del square x by del y square, like that. So, these are the notations that is used here. Okay. Okay. And obviously, we assume that there are appropriate boundary conditions available actually. Okay. Depends on the situation. Sometimes value is fixed, sometimes derivative is fixed, and things like that actually. And one end can be value fixed, other end can be derivative fixed, and depending on the application really actually. And the objective is that x of t y should go to something like x star of t y as t goes to infinity. So, that means this x star of theoretically speaking, this t does not mean too much of sense, because t goes to infinity already. So, we have something like a x star of y. Okay, let us say I want it to happen something like this actually. Y goes from 0 to L. Okay, and I want this to behave like this. This is something my y star actually, sorry, x star is a function of y. Okay. So, this is my y and this is my x star, let us say. So, as time evolves, okay, any arbitrary initial profile should finally come and converge here. That is the ultimate objective actually. Okay. Alright, so how do we do that? First of all, we define an error. Error is integral value we integrated all over the spatial domain. So, x minus x star, whatever is the error, suppose this is not the case, but your x is somewhere different, okay, something I do not know what form, is something like this actually. Let us say this is my x actually, this is my x star. Okay. Then what you really see is this difference, what you see this difference it has to go to 0 with time. Okay. So, how do we make sure that this difference go to 0? First we define something like error quantity, okay, z of t is integrated square error, okay, over spatial domain, and then if this goes to 0, okay, remember everywhere it will go to 0, because this is a quadratic function actually. Okay. If somehow z is pulled to 0, then everywhere else this error will go to 0, and hence the objective will be met, whatever objective we are talking actually. Okay. Anyway, so design a controller such that, so what is the idea of, following the idea of dynamic inversion, tell okay, we will design a controller such that this error dynamics will be satisfied. K is a positive definite matrix, okay, in general, or if it is a scalar, it is a positive number. Okay, K is a positive definite matrix in general, depending on how many terms are there in Z actually. Okay, but just to make sure that ideas are simple, we tell this is scalar, so K is a positive number actually. So, we enforce this error dynamics, so that the solution of this obviously is Z of t is e to the power minus k t into Z naught. Okay. Initial condition is Z naught. So, this obviously will go to 0, okay, because of the exponential term that is sitting here actually. Okay. So, that is why we want to enforce this error dynamics here. Now, it is the rest of the things are typically math. So, from this equation, okay, you put the definition of z, that is like that, z dot which is del z by del t, remember this is a spatial integral. What you are talking about is a time derivative. So, this time derivative can be pushed inside the integral, and then you can put here is x dot and things like that, and x dot can be brought in, that all the system dynamics that you know here, and carry out the subsequent algebra, and it will ultimately result in this kind of an equation actually. It will give us something like this, where gamma is defined something like that. Okay. Now, the question here is, we have a control to solve from this equation here, and if you really see that this equation, okay, what you see in the right hand side is a scalar, but what is u? U is a controller that acts throughout actually. Okay. U is something like a profile. That means, if you see in a grid point sense, that is actually infinite number of points actually. Okay. So, that means, this equation what you see here if you really want to solve for u, it turns out it is a very highly under constrained problem actually really. Okay. So, then you have to do some further algebra to get a solution for u, because there is no unique solution really. Okay. So, now what you tell, okay, if you can do that, there are many solutions, then we want one solution which is control minimizing also. We do not want to kind of keep on getting some solution arbitrarily. Okay. We want that particular solution which will be minimum magnitude actually. So, obviously, the idea here is to minimize this cost function. So, we want to minimize this cost function subject to this constraint equation actually. Okay. Then you can have this augmented cost function coming from this part, I mean this r times u square coming here plus lambda times all that, and then subsequently the necessary condition will tell you that first variation has to go to 0. Then there is the first variation, this is where the variational calculus comes in. The first variation you have to expand based on this expression of j bar, do it carefully, okay, you can derive it yourself also, term by term you have to do, and then this has to be equal to 0. Okay. Now, if this has to be equal to 0, this expression, and we know that variations cannot go to 0, that means del u and del lambda cannot go to 0, because they have to satisfy this for arbitrarily taken arbitrarily large number of variations, this condition has to be satisfied. So, hence the variations themselves cannot be 0, and hence if you excite that calculus of variation fundamental result, if such a situation happens, then the coefficients have to go to 0 basically. We have talked about that theorem in one of the early classes actually. So, this has to go to 0. Okay. So, that means this equation will get it here, because variation this del u cannot go to 0. So, rest of the thing will go to 0. So, that is how we will get that. Okay. No, sorry, that is how you will get this coefficient has to go to 0. Okay. And then that is how we will get actually. So, from here, okay, what you get is this integral this quantity up to this, okay, is to be equal to gamma, okay, because this cannot go to 0. So, the coefficient has to be 0. What you see in square bracket has to go to 0. What you see in square bracket has to go to 0, like that. Okay. Once you put that, then I mean you got a solution ready in a way, but because you have to solve these two equations for lambda and u, and then you get the solution. I will give that expression in a moment. But under steady state, what happens? When the steady state is reached already, then this has to be like this. This has to satisfy the same system dynamics. Otherwise, if the profiles do not satisfy the system dynamics naturally, then there will be deviations actually. So, obviously, that we do not want to happen. So, obviously, this condition has to be satisfied actually. And the claim here is when x goes to x star, u should go to u star also. Then only it can be maintained there. The error can be maintained at 0 basically. Okay. So, from this whatever solution we will get, it goes to 0 actually. Okay. And the solution turns out to be something like this form actually. Okay. Okay. And in a special case, okay, if you solve these two equations, and you can see the details in the paper if you are unable to see that, and then you can come up with this solution actually. And under a very special case where r of y is just a constant, you do not give differential emphasis of controller values, magnitudes through the spatial domain, then it will result in somewhat little more simplified expression actually like this, okay, where g turns out to be a constant quantity and r turns out to be a constant quantity as well, then it will result in something like this actually. Okay. So, you can note that the control solution is actually happening in closed form. So, that is a good advantage actually. Okay. Now, the claim here is if you get a steady state control like this and you have a time varying control like this, okay, whatever either this way or that way, then I mean there as this profile develops towards x star, x goes to x star, then u should also go to u star. That means, there is no singularity in the control expression. Remember, this is not singular as long as g star is not singular. Okay. And obviously, system dynamics will be well behaved, otherwise the system dynamics itself is not well behaved, modeling has some problem, okay, in general. So, if assuming that this expression has no problem, then you will go to that expression and hence there is no problem actually. Okay. The behavior is the proof is also given here. You can tell that, okay, as a very special case, what you do is as a very special case, you take 0 to L in y dimension, tell, okay, everywhere else it is 0, but there is a small domain and around which it is not 0, and let that be something like y naught actually. Okay. So, then around that y naught what is happening and all that, this analysis you can carry out. I think I will not go through the details here, it is not worth probably. but you can see the paper and then carry out this algebra yourself, and then realize that ultimately this this u bar, which is the average control in that small domain, whatever it you are coming, as long as this is something like, okay, the philosophy is like this: you construct a y naught and construct to, I mean, you are analyzing something like epsilon by 2 this side and epsilon by 2 the other right side actually. So, what will happen in this situation, and ultimately you come up with some expression, and the claim here is when epsilon tends to 0, then x will tend to x star obviously, and then you will also, this u bar, which is average control over this domain, will also approach to that this expression u star actually, and when epsilon tends to 0, obviously it will match there. Yes, that's the whole idea there. Details you can see in the paper actually. Alright, so this is the concept here. Finally the control expression, something like when x is equal to x star or a very close domain, actually x is very close to x star, then you can switch over to the simplified expression. Otherwise you can implement this way, okay, and remember these two are equivalent expression. So, when there is equivalent expression, you do not want to kind of unnecessarily keep on computing actually. So, that is why there is a simplified form here. Otherwise, there is no singularity per se. You can still keep on implementing this, nothing will happen really actually, which is not the case when you have discrete actuators actually, which I am going to show you that very shortly. Okay. Now, a small motivating problem, there is a heat transfer in a fin, okay, there is a fin here, there is a heat transfer here, and here we are assuming all sort of heat transfer, that means conduction, convection and radiation, and there is a source which is coming through the wall and all that actually. Okay. So, this kind of modeling will excite nonlinear behavior also through that actually, okay, and depending on the situation, how much nonlinearity on will depend on the alpha 3 quantity actually. And ultimately what we really need is a steady state profile, and steady state profile we need something like this. Obviously, there is a root. This is something like a fin for heat dissipation actually, okay. Many times this heat dissipation fins are used in various mechanical devices and all that. So, inside this there is a tube sort of thing, and these fins are protruding out just to dissipate the heat actually. So, because there is a source inside that, so obviously the wall temperature is expected to be slightly better than that, because it is kind of unnatural to assume that it will be throughout the same spatial domain, it will be same. We can do that with heavy emphasis on control and all that, but practically it may not be a good idea to do, may not be that easy to do also actually. So, we assume something like this, which is very much reasonable. Okay, the wall temperature is something like 350 degrees centigrade, sorry 150 degrees centigrade, and slowly it will come to something like 130 degree, I mean as with spatial domain sort of thing. Okay, 20 centimeter away it is 130 actually. Yeah. So, if you have that, then the other tuning parameters are there. This is the kind of results. If you start with initial profile arbitrary whatever it is, and ultimately it will come to a profile that you want actually. This is the profile, this is the space y. So, this is the what you want it in this form. Okay. So, it is happening, okay, and associated control history has to be given like that. So, this is with respect to a sinusoidal profile as initial condition basically. Okay. Now, something like, okay, whether that is happening or not happening, you can put the deviation history also, okay, the error of the temperature profile and all that, and you can see under steady state how closely they are matching actually here. Okay, it will come and exactly kind of do what you want to do basically. And some arbitrary profile, if it has random initial condition, then also it will come out, okay, that this is the control part of it, but it will also come out that the error goes to 0 everywhere actually. So, again it will be what we really want actually. Now, going to the next part of it, which is like distributed parameter system control using ODIs with a set of discrete actuators. This is more practically relevant, because continuous actuator, even though you get nice results like that, how do you actually implement this controller throughout the time? This is evolution of time and this is evolution in space. So, every time you have a nice mathematical solution, but may not be possible to implement actually. So, here we want to address that concern and then tell, okay, how about discrete set of actuators, set of discrete actuators actually. So, you have fixed location sense, you have this controller 1 here, 2 here, 3 here like that actually. Okay. Then what do you do? Now, at m y equal to ym, analyze the situation. Okay, we have this finite width controller sort of thing, which I tell everywhere else may not be there, but it is a set of discrete actuators. At y equal to ym, we have something like a constant control um bar, okay, which is ym minus wm by 2, okay, ym plus wm by 2. That means the width of the controller is something like w actually. Okay. Alright. So, if you have that kind of thing, okay, so then what to do? Um bar is constant and outside the interval it is 0 basically. Within this interval it is some value, outside that is 0. Okay. And also we assume that there is no overlapping influence actually. Obviously, that is also a practical constraint. How can you have a overlapping actuator basically? That means this next controller will be situated far away from this one. So, the actuation sense these are all independent actually. Okay. And also we assume that there is no boundary control action, which is actually a rather little bit strong assumption. Typically, boundary control is a subject of topic, because even more relevant in partial differential equation. Suppose you want to control a vibrating string, probably you want to hold it at one hand and then vibrate it at one end actually, one end of the string, and so that it will ultimately take it to that shape sort of thing. So, those are boundary control problems, but here you are assuming that there is no boundary control, everything happens inside the spatial domain in discrete sense. Objective still remains same, x should go to x star, okay, for all y. And then again we similarly define an output vector, okay, and we also design a controller so that this aerodynamics is satisfied. So, until this point everything remains same. Again we will end up with some constraint equation like that. And here also remember you are talking about single equation, but you have a many number of controllers but which are finite actually. So, U is not like spatially distributed control infinite dimension, but you have a set of discrete actuators U1 bar, U2 bar, things like that actually. So, if you expand this expression, okay, and then write this equation in terms of U1 bar, U2 bar up to Um bar. So, this is the expression that you can write actually. Okay. So, at grid points 1 to 2, 3, 4 up to M, capital M, we have these control actuations which a small width W basically, and in that we are assuming there is a constant control actuation actually. Okay. So, the IMs can be computed that way, but U's are my control input variables that I want to compute actually. Cost function, obviously this is also under constraint problem, because there are several freedoms and constraint being lesser. We want to have a cost function optimization. So, this is a cost function, again we assume like that. Again the minimum values of control throughout the domain, but we can have relatively weight up or down depending the values of R1 to Rm actually. Okay. All right. Well, there is a small print mistake again. This is to be capital M. Okay. All right. Now, the final solution turns out to be like this. Okay. And if you assume that this R1 W1 is equal to R2 W2 and things like that, they in combined sense they can be equal. Right? For example, if you assume all width of the actuators are same and all weightings are same, that means R1 is equal to R2 equal to R3 like that, and W1 equal to W2 equal to W3 like that, then all these values are also anyway satisfied. But in general, the mathematical condition required is something like this: R1 W1 is equal to R2 W2 like that. Okay, if this condition is satisfied and this moment of inertia is this vector I1, I2 up to Im, okay, then if this control turns out to be of this form in a special case actually. Okay. If this condition is satisfied, this is not satisfied, then this is the one actually. Okay. All right. So, this is what it is. So, now we want to have a solution, so which will give minimize this cost function subject to this constraint equation, and the solution is also available in closed form actually. Now, there is a problem here. The problem turns out to be like that: when as all i's goes to 0 and gamma is non-zero, then will blow to infinity. Okay. Now, if you see this, when will that happen? Now, remember the expression for y and all that, i's and all that. When x goes to x star, then I will go to 0. Okay. And x going to x star is our objective. We can't escape from that. That means that has to happen asymptotically basically. So, when this starts happening, our objective starts happening, okay, then we are starting to have some problem actually. But it has to have, because remember this denominator, fortunately there is a norm square sort of thing. That means this norm will go to 0 only when all these i's go to 0 together. Not that one I will go to 0, every something will happen. No. All i's have to go to 0. That means everywhere in that this domain where the control actuation is happening, this width W1, W2, W3 up to Wm, everywhere those segments have to go to 0 actually. Okay. Then only this problem will happen. Okay. Now, this happens when the objective is met. So, at that point of time we tell, okay, if the objective is met, then why formulating and then why getting ambitious and telling that, okay, through this control actuation I will be able to control in other domain also. It may not happen actually. because there, I mean, wherever control is actually located, there I should see some error at least actually. Okay, if nowhere else I see an error, then it becomes some sort of a observability problem, and error is not there. So control remains a kind of silent actually, because it thinks, okay, I mean, the objective is met sort of thing actually. Okay, so and if you really want to control it through, I mean, the errors in the other domain, because the errors are 0 here, that means the control effectiveness is 0 at that point of time, at that point in space. So the every control starts blowing up actually, it goes to infinity actually. Okay, that's the physical reason for that. So then we tell, okay, if that is the case, and that point of time we will have a revised objective. We will not aim that everywhere it should go to 0, but only those points where the control, I mean, where the actuator is located, at that point we will continue to hold the state values at the desired values basically. Okay. So if you have that, then if you define a state vector like this, x1 to xm and x star is something like that, and tell, okay, my x has to go to x star in discrete sense. It may not happen everywhere, I do not want to see that, but in this domain, because I do not see any error in the state, I will continue to hold that basically. Okay, so that is the objective there. So if you have that, then again you can have this error dynamics getting enforced here, like dynamic inversion sort of ideas, and then you can in nth channel this equation will sit, and hence you will get a control like this actually. Okay, and this the other control does not boil down to this, by the way. Okay, there is a different objective actually. So we have to take a call sometime when to shift. Alright, so implementation sense, this is something like this. If I2, this norm of I is greater than some tolerance value, then use this, but if it is less than some tolerance value, shift to this, and this shifting does not happen in a smooth way really. Okay. So you have to take a call of this number of tolerance what you want to put there actually. So again going back to the same heat transfer problem, because it contains nonlinear terms and things like that. And this is also as a mixed boundary condition. Remember, at y equal to 0, there is a wall temperature, but at free end, the derivative is 0. That means this free end is insulated actually. Okay. So that I forgot to tell, but this is what it is actually. Okay. So one side it is Dirichlet boundary condition, other side it is Neumann boundary condition actually. Alright, so desired temperature again remains same. So system dynamics is same, objective is same, only that the control actuation is not continuous, but it is a finite set of actuators actually. So now using these formulas what you just derived, and you assume 5 control actions are there, and remember everywhere it is constant. Okay, whatever this grid point you are talking, this have to be constant, and in between there is no control. Control happens only here a little bit, here a little bit, here a little bit, like that actually. And here you see some sort of a discontinuity, that is where there is a control switching. Okay, we want to switch from one control to the formula to the other formula actually, and also see that it is happening, but not in a very good way. There is some sort of waviness. Okay, the error is not going to 0 everywhere. Okay, some sort of, it is roughly happening, but not happening in a very good way, which is also expected, because you really want to control an infinite dimensional system through a finite dimensional control. Obviously, your capability is lesser actually. So what about increase and doing an experiment? Again, these are numerical experiments anyway. So doing an experiment with 10 actuators rather instead of 5. So somewhere this wavy nature has to go, and it does happen actually. If you take 10 actuators, and the wavy nature is much more smoother. Okay, you can put much lesser tolerance value, because remember the singularity happens only when this goes 0 everywhere actually. Okay, all of these control, I mean these integral values has to go to 0, then only this control will go to infinity, otherwise no. Okay. So this is much better. The more and more number of control actions you have, we have that many freedom, and hence you can do a much better job, engineering sense basically. Alright, so that is nature, I mean it's expected sort of behavior basically. So again this is a random profile, and we stick to 10 actuators again because of this behavior sort of thing, and then if it is a random profile, again it is able to cater for that actually. This is the control behavior, and finally you see the temperature, desired temperature is met actually. And this kind of repeated, see this is once you write a code with randomized initial condition, which can be done using Fourier series and things like that, you can run your program repeatedly. Well, every time it can pop up some randomized initial condition, and then let your simulation happen through your control design action actually. So every time we will end up with something here actually. That exercise you have done many times, and the many initial conditions you verified and all that actually. Alright, so similar results have been obtained from numerous random initial condition actually. Alright, so the conclusion sense of this particular approach is actually a new technique which did not exist in the literature. We propose for the first time, and essentially it brings it proposes a new idea of distributed parameter system control using dynamic inversion, which is a nonlinear control theory, the control synthesis theory using feedback generation like that, plus optimization theory. Now, these two are coming together to propose a new idea there. Okay. Alright, it falls in this design then approximate philosophy without too much of math complexity actually. Once you understand dynamic inversion ideas, which again I emphasize, if you don't know, then I suggest that you see one of I think couple of my lectures in my other course on dynamic inversion, then it will even make more sense actually. Okay. So, it actually falls in the design then approximate because I mean what you are telling is in the development we are not starting with this finite number of grid points and all that. Start with the whole spatial domain as it is, did some spatial integral and things like that. Ultimately, you have a formula, and then when you implement, then you discretize and all that actually. So, that falls onto the design then approximate. But it does not it completely avoids this infinite dimensional operation theory, and hence it is not mathematically complex actually. Also leads to closed form solution, and hence there is no computational complexity issue. And then in continuous actuator case, there is theoretical elegance, that means guaranteed convergence is there, and there is no control singularity problem. However, in discrete actuators case can also be solved, which is practical relevance actually. Okay. And successfully it has been demonstrated for a nonlinear program. That heat transfer problem contains radiation terms also, which is 4th power of temperature actually. Alright, so with that I think I will stop this lecture. Thank you.